Anybody? I have to say, I am not a great lip reader. Let's listen to what it was, knowing that MobiVSR predicted difficult. Difficult. All right, so that's the problem. And Nilay will now start to tell you about the solution.
Good evening, ladies and gentlemen. I'm Nilesh Srivastav. I recently graduated from University of Delhi. And to be very honest, this is my first talk at a conference. So I'm quite nervous. I'll try not to screw this up. With this disclaimer, I'll start talking about how we developed the MobiVSR model. So it's only appropriate to first look at what the state-of-the-art model is. The state-of-the-art model while we were working was by Stefailakis et al. Published in 2017, which is essentially a ResNet plus LSTM model. If you look closely, the model uses 3D convolutions, it uses ResNets and lots of LSTMs. So naturally, we started by analyzing the bottlenecks which were present in this in the previous model, and the graph which you see over here basically gives you an idea of the time being consumed by the convolution layers used in the Stefailakis et al. Model. There were three primary observations which we drew from the profiling experiments which we performed on the LSTM plus ResNet state-of-the-art model, and these were as follows. The first, the major bottleneck in that particular model was the stack of residual blocks used in the state-of-the-art model. The second primary observation was that amongst single layers, 3D convolution takes the maximum amount of time. And finally, the sequential processing of the LSTMs being used in that particular model is also a major hog that really slows down the state-of-the-art model. So our approach was to tackle all these 3 points one by one. So we started with trying to optimize the stack of residual layers by introducing a new kind of a layer which is called the shufflenet operation. And the origin of the shufflenet operation is from a paper by Parley Lab at UC Berkeley. You can see it for further details. But the essential idea is this. You basically interchange the channels of the incoming input, and what it does is, what it turns out that you do not, in spite of not having extra parameters, it really performs quite closely like a convolution layer with respect to accuracy. So what we did was we included this channel shuffle operation in the residual block in MobiVSR, and our residual block looks something like this. So on the left is the residual block we use when the size of the input and the size of the output is supposed to be the same, and on the right is the residual block we use when the size of the input, we reduce the size of the input. So basically, we are reducing the size of the input using the Con2D layer in the right-hand side. So talking about how we optimized 3D convolution, we took inspiration from 2D depth-wise convolution layers, which has been used quite effectively in mobile-net models. So our idea was to extend this. For the first time, we extended this particular 2D convolution to 3 dimensions, that is the 3D depth-wise convolution layer. But although as easy it may sound, it's quite difficult to really pinpoint or to really formulate how one is going to extend 2D convolution to third dimension. And that's because you have basically 3 important things to, like 3 degrees of freedom, which you have to experiment on. First is how are you going to factor along the channel dimension? Will you factor along both the channel and time dimension, which will reduce the parameter point count by a lot? And finally, are you going to reduce only by the time dimension? So by performing various experiments, we found out that the third technique works. It gives the best accuracy and size trade-off. So our 3D convolution layer, which we are going to use, the 3D depth-wise convolution layer, which we are going to use in MobiVSR, is essentially a 2D depth-wise convolution layer along with a factorization in the time modality. So, because the 3D depth-wise convolution basically has a 4-dimensional size, we cannot really represent it on a 2D plane. So, for reference, we have included the underlying operations in a 2D depth-wise convolution layer. It's somewhat similar and analogous to what is happening in a 3D depth-wise convolution layer. You just need to remember that we are factoring along the time dimension. And finally, since LSTMs are major hog, we did away with LSTMs, and that was because there was this paper titled Temporal Convolution Neural Networks, which stated that you can replace LSTMs in some cases with 1D convolutional layers, and the accuracy, and you do not lose accuracy by a large margin, but you do increase the efficiency of the model. So overall, our architecture looks something like this. So we have the front-end part, which is essentially a feature extracting part, which includes the 3D depth-wise convolution layers. We have the stack of residual blocks in the center. And finally, we have the backend, which essentially takes input from the residual layers and classifies into and gives out the probability to choose amongst the 500 vocabulary given in the LRW data set. An important point to note is that if you see closely, you'll find that I mentioned a parameter called alpha. It's basically a structural parameter, because we believe that one model would not fit all use cases. So basically, you can vary this alpha and increase the size of the model if you want to increase accuracy. And you can do away with little, and you can give up some sort of efficiency. So this is how the residual block in the stack of residual layer looks like. I discussed it earlier as well. And now my colleague Astitva would be talking about about the evaluation aspect of MobiVSR. Thank you.
Hello everyone. So I'll be quickly moving on to the evaluation of the solution. So we use the lip reading in the wide data set for this. So it has around 5 lakh training videos, and it has a wide variety of illumination and head pose variation. So that's what makes it challenging. So there are videos which are 1.16 seconds of length, and each of them have 29 frames. So it has the region of interest in its center. So we didn't need to do any pre-processing before that, but that can be developed with lip-reading architectures. So these are the results we obtained. Here MobiVSR, the number which is alongside MobiVSR denotes the value of alpha. So alpha is basically a parameter which would for the trade-off between the model size and the accuracy. So as you increase the value of alpha, it would increase the number of residual blocks which are in the architecture, and hence we are able to achieve more accuracy, but at the cost of the model size. We perform significantly better, as you can see, from in terms of flops as well as the parameter counts. So this is the variation of accuracy when in terms of the parameter count which we have. So that's the top 1 accuracy and the top 3 accuracy. More details can be found in the paper. Another calculations which we made were of the carbon emissions, which is also a crucial point. Based on the work of Struble as presented in ACL 2019, we calculated the energy consumed by the model per inference and the CO2 emitted. So it performs significantly better. So these are some of the commonly mistaken words. Like benefits and benefit, they have a similar lip movement, and hence it's difficult to distinguish between them. So the confusion matrix for this was also evaluated and is in the appendix of the paper. So the applications of lip reading include building systems for people who have hearing loss and recreating speech in the noisy environments. It can also be used for security and crime investigations. So the current drawbacks are that it has a restricted vocabulary. So it has a set of 500 words which can be further expanded with the data set. There are some security risks which are associated with the unethical usage of it, and like I said, it fails to distinguish words which have different phonemes, like a similar lip movement, so that's what we leave to future work. Thank you. You can find the paper and the code at those links, and we have a working demo as well. So if you guys want to see that, you can contact any of us for that. Thank you.
Okay, any questions? Okay.
Thank you for that talk. I was just wondering, you talked about using the LRF, the lip.
I think the mic.